we're going to use half-life and the repetitive part of this to solve a couple problems. So this is carbon-14 has a half-life of 5,730 years. Complete the chart below that shows how many years go by and how much carbon-14 is left until I get to 3.125%. So this side of this table is always going to look the same. We're going to start with 100% of it remaining, and that takes 0 time. And then we have 50%, and half of 50 is 25, and half of 25 is 12.5. And half of 12.5 is 6 1/4, and then half of 6 1/4 is our 3.125. Should have used one more row on this or left off my 100%. Now, time passed. Well, the first half-life is 5,730 years. My second half-life is plus 5,730 years, right? So I went from 0 to 5,730 to get the first to decay. Now I've got to have that again, so 5730 plus 5730 is 11,460. And then I've got to add that another 5,730 years to it, because that's how long it takes for the next half of it to decay. So 17,190, and then another 5,730 gets me all the way to 22,920, and then finally to get to 3 1/8% left, I've got to add on my last 5730 and get 28,650. So 28,650 years from times 0, we get to 3.125% of the carbon-14 remaining. And that's because every half-life is the same amount of time, 5730, and it doesn't decay the same amount of stuff, it always decays half of what's there. So how old is a sample that has 25% of its carbon-14 remaining? Well, that's easy, 25%. That happens after 2 decays. 2 decays takes 11,460 years. Cool. Another one, create the graph that goes with this. So down here we're going to have time, and over here we're going to have percent, right? And so again, I have 100%, I have 50%, I have 25%, I have 12.5%, I have 6 1/4%, and then I have 3.125%, and then time. For carbon-14, my time scale looks almost the same as my 2-minute scale in the previous lesson, except instead of calling it 2 minutes, right, there's 5,730 years. Here is 11,460 years. Here is 17,190 years, 17,190, then 22,920, and then 28,650. And so each one of these are 7,000 or 5,730 years apart. Then I'm going to plot my points. So here's times 0, 100 years, 5730, 50 years, 11,960, 25 years or 25%, 17,190 years, 12.5%, and then 6 1/4%, and then 3 1/8%, and then we can just connect up our dots with a nice smooth line, and we see this exponential decay through time. So pretty straightforward process on that. They're all the same. So oxygen 22 has a half-life of 2.25 seconds. So after 2.25 seconds, we will have 50% left. And then after another 2.25 seconds, or 4.5 seconds total, we will have 25% left. And then after another 2.25 seconds, or 6.75 total, we will have 12.5% left. And then after another 2.25, we will have 9 seconds total, or 6.25%, and then finally we add our last 2.25 to this and get 11.25, and that gets us to our 3.125. Like I said, this is the same every time because we just keep cutting it in half. After 9 seconds, we see that there will be 6.25% of our oxygen 22 left. And when we go to graph this, it looks just exactly the same. Your time is just going to be on a different scale because it's got a different half-life. Okay, so again, radioactive decay does not occur at a constant speed. Decays in half-lives, and each sample takes the same amount of time to decay, even though there's, for half of it to decay, even though there's less of it there.